Hello. Just a couple of little bits to add to our understanding of potential energy diagrams. The first thing is, so we've seen that some reactions are reversible, meaning that the products can collide and go back to the reactants. And so on a potential energy diagram, we can figure out both the activation energy and heat of reaction for a reverse reaction in a very similar way. So let's look at this endothermic potential energy diagram right here. We know it's endothermic because overall it's gaining energy. The activation energy, remember, is the energy you have to add to break the bonds. So if we start at 10, we have to add 70 to get up to 80. So this is 70 kilojoules. The heat of reaction is the difference between where you start and where you finish. So if we start at 10 and we end at 40, that is an increase of 30 kilojoules. And since it's gaining energy, that's positive. To figure out what the activation energy of the reverse reaction would be, we're basically, instead of starting on the left-hand side of the reaction, which is normally the reactant, we're going to start on the right-hand side. We're starting with our products and we're going back to our reactants. So in this case, we're already at 40 and we only have to go up to 80. So we only have to add 40 more kilojoules to break the bonds if we're going in reverse. So the activation energy for the reverse reaction is 40 kilojoules. For the heat of reaction, remember, since it's the reverse reaction, we're starting on this side. So we're starting at 40 and we're going down to 10 this time. So instead of gaining 30, if you're going in reverse, you're losing 30. So this, to show that we're losing 30, I'm giving a negative sign. So a pattern you'll notice is the heats of reactions are the same but opposite. So, and that's because it ignores the hump in the middle and you're either gaining energy or losing energy. And it's the same energy either way. The heat of reaction, the activation energy is going to be different because the hill has a different height depending on which side you're approaching it from. For an endothermic reaction, you have to add more energy in the forward direction than in the reverse. So that's just a little thing. You're going to have a couple questions about that. The other thing I wanted to show you is in your reference tables, table I, heats of reaction, and then at 101.3 kPa, and this is standard temperature and pressure. This is under like normal conditions. This is the heat of reaction for all these different reactions. And you've got a whole list of different reactions. I want to start by pointing out probably the most helpful information at the bottom. On your reference tables, they actually tell you, they remind you, a minus sign indicates an exothermic reaction. So that can be really helpful if you ever forget whether positive or negative, because what'll happen is they'll just tell you the delta H of a reaction. They won't give you a potential energy diagram. They won't tell you about the temperature going up or down. And based just on that delta H value, you'll have to decide whether it's endothermic or exothermic. So if you just remember minus sign is like, if you just know this is here, you can always check to see that you're remembering it correctly. And then if you have your reference tables with you still, I'm sure you pull them out and look at them every day, right? You can write all over them, or at least write them how I did. The reactions on this table are broken up broadly into 3 categories. So this first section here is all combustion reactions. It's all organic molecules like methane and propane, octane. These are alcohols, methanol and ethanol, sugar. So, and they're all combining with oxygen gas. So they're burning and releasing smoke, carbon dioxide, and water. And one thing you notice, all the delta H's are negative because combustion is an exothermic reaction. Energy is coming out, and you can see that combusting different starting materials releases different amounts of energy. So if you want to release, notice how like octane, like what you would find in gasoline, high octane fuel, releases lots more energy than like propane, like the gas that's used in grills and stuff. So that can be useful. The next section is a bunch of synthesis reactions. Remember, synthesis is combining elements together to make compounds. So you have a mix of exothermic and endothermic reactions, and whether they're endo or exothermic has to do with the energy of the bonds, which has to do with the electrons and a lot of stuff that we don't worry about in high school. One of the interesting things you can use this for, and if you were taking the Regents, which you're not, but if you ever do take the Regents, when they want to be tricky, will ask you about decomposition reactions. And they'll be like, what's the heat of reaction of like the decomposition of water? So you would have to look up on the table, well, I know that the synthesis of water going forward is negative 483.6. So decomposition would be the reverse of that. And I know the reverse would be positive 483. They would do that to you, but they're not this year. But the CASA learning assignment might. So this section is for the synthesis and also decomposition reactions. And the last section, these are all salts dissolving in water. So if you look, these are all solid substances. They're being added to H2O, and then they're breaking up into their positive and negative ions. And this little AQ, you remember, stands for aqueous, which means dissolved in water. So all of these salts dissolve in water, breaking up into their individual ions. One thing you'll notice, a lot of these are endothermic. These will actually get colder. And this is how, like, this is cold packs. Cold packs will use like ammonium chloride or ammonium nitrate in cold packs. Like you mix them up and they get really cold. True story. All right, take care. Good luck. Bye.